Hello and welcome to the video lecture series on thin film flow modeling and simulation in the course M7033T Scientific Computing with Applications in Tribology. My name is Andreas Almqvist and I work at the Division of Machine Elements here at Luleå University of Technology. Now this is the second part of the third video lecture on hydrodynamic cavitation, and here you'll learn about cavitation modeling and how to pose a complementarity problem for constant bulk modulus type of fluids. Let us assume that we have a constant bulk modulus type of compressibility in our fluid. Then we can build up a cavitation model for this, which actually can consider as many occurrences as you like of rupture and reformation within the lubricated conjunction. So this can be done by defining the density as the cavitation density, meaning that it's the density at cavitation pressure, which is typically the atmospheric pressure, but might be a little bit lower than that. And then in the fully saturated region, it is given by the constant bulk modulus type of compressibility, but in the cavitation zone, it's just the cavitation density times the time. So this means that in the cavitation region, the density is just rho c times the saturation, and therefore vapor or air density is neglected in this zone. So we have that definition of the density. We assume that to hold. Then we substitute it into our expression for the mass flow. So we just replace theta in our mass flow with the expression for theta that we can obtain by just dividing rho with rho c. And then we have in the fully saturated region we have one expression, and in the cavitation zone we have another. But remember that the gradient of P is constant in the cavitation zone, so it simplifies to only be a mass transportation term in the cavitated region. What follows now is a quite mathematically oriented section in which we will carry out two changes of variables, and finally we will obtain a very neat expression for the mass flow. So let's start. We know that the mass flow can be formulated in terms of the saturation theta and the pressure P, like this. However, if we make the following change of variables, we define U to be dimensionless density of theta minus 1 instead, then we can write the mass flow like this. Perhaps doesn't look very much more simple, but it will be very nice in a complementarity type of sense, as we now have made u to be larger than 0 and not as theta larger than 1. Okay, so we subtracted 1 to have u more like a complementarity variable, complementary variable in a complementarity problem. So we note also that the following relations are fulfilled. So when we are in the full film region, the flow is fully saturated, u is larger than 0, and u is actually 0 when we are in the cavitated region. Directly from the change of variables, we obtain an expression for the gradient of u in terms of the gradient of p, and we can make more simplifications of our mass flow, of course. So now we have a mass flow in terms of u and theta, and there is no more p in there. And we remember that in order to obtain this, we have made the following change of variables, and the following relations holds. Now we come to making the second change of variables, and this is to have another complementarity variable. And here we make eta to be 1 minus theta, which means that in the full film or fully saturated region, we have eta equals 0, and otherwise it will be 1 minus theta. So it will be 1 minus theta when u is 0. And now in terms of eta, u and eta, we have a new formulation of the mass flow, and we have the following relationship between relations with the variables, and they are that in the fully saturated region, u is greater than 0 and eta is 0, and when u is 0 in the cavitated region, then we have eta, and eta is larger than 0, but it's actually also constrained, so it's less than 1. And this makes u times eta always equal to 0, as you see. So we have these relations. Now the piecewise expression that we have for the mass flow in terms of u and eta, which can be converted into a single expression for the mass flow, as you see here. In the full film region, we have u larger than 0 and eta equal to 0, and therefore the last term is crossed out, and we have exactly what we had before in the piecewise expression, as you see here above. Same thing goes in the cavitated region, where u equal to 0 and eta is larger than 0. We also have terms cancelling out in our unified expression, universal expression, and we end up with the same expression as we had before. With the expression for the mass flow obtained before, we can now formulate a modified version of the Reynolds equation by just ensuring mass conservation, i.e. In the stationary case, we should have the divergence of q of the mass flow equal 0. So it's just to take our expression of the mass flow and put the divergence of it equal to 0. However, there are constraints, both for eta and u, and the full problems, including those constraints can be written like this. So we've taken the expression above and formulated it a little bit differently here, just in order to make another comparison later. So we have the mass flow, which we have now made an equality with the left and right hand side like this, and we have the constraints below, and this shows truly really that this is a complementarity problem, precisely as the contact mechanics problem we learned before. So in hydrodynamic cavitation, we can formulate a discretized complementarity problem which looks very, very similar to the problem that we found for the contact mechanics case. So finally, having solved the complementarity problem for the complementary variables u and eta, we can just use the change of variables for u and for eta to obtain the pressure and saturation, and we're done. In some very simplified situations, it's possible to obtain an analytical solution. One such example is given here. So it's a pocket bearing. You can see the geometry here on the top right, and it's described by this piecewise expression for the film thickness. Solving that by means of the LCP, the Lemke algorithm to solve LCPs numerically, will give us a solution which, if sufficiently well resolved, it will resemble the analytical solution very well, and that you can see here in the figure on the lower right, where we have plotted the pressure both for the analytical solution and the numerical solution, and as you can see, they are visually nearly indistinguishable. So this concludes the third video lecture on hydrodynamic cavitation in the series of thin film flow modeling and simulation. And next up, we will look at the discretization of the thin film flow problem.